Here I am in B327, and I'm going to do a Hess's Law practice lab. This is another case of using Hess's Law in a lab. I think you can see it, look at the calculations here, and then you're going to see how your lab compares and doesn't compare, but you can use at least the parts that are needed as a model for this. And it'll give you a couple of different perspectives on a Hess's Law type of lab. So here we go. In this one here, and you do have the photocopy for this so you can look this through, we're going to look at three reactions involving sodium hydroxide solid dissolving in water, sodium hydroxide solid dissolving in hydrochloric acid, which is aqueous, and then aqueous sodium hydroxide dissolving in aqueous hydrochloric acid. And we're going to look and realize that reactions 1 and 3 should add up to equal reaction number 2. But here's a procedure for doing reactions 1, 2, and 3. You can look at that a little bit to see the amounts and how they worked. Here would be a data table. I'm going to go right to these three reactions and show how Hess's law works here. So the first one, we're taking sodium hydroxide solid, putting it in water, which would make these two things aqueous. Now, a lot of times when you dissolve something in water, it feels a little bit colder because that's an endothermic process, not with sodium hydroxide. It's clearly an exothermic process. It gives off energy. Okay, I'm going to skip to reaction 3 where we actually take a solution of, I believe it's 1 molar NaOH, 50 milliliters of 1 molar NaOH in 50 milliliters of HCl solution. And that would also be 1 molar. And I combine those and I get a neutralization, okay? Because I'm taking the base NaOH, the acid HCl, I get water, and then I get a salt left over. And neutralization reactions will typically be exothermic because they're very favorable for form the very stable product of water, and that gives off energy. Now, the last reaction is really a combination of the two things. But in this one, in the lab part, I actually take solid sodium hydroxide and then add that instead of directly to water, I add it directly to the 1 molar hydrochloric acid. So what happens is the NaOH first dissolves in this aqueous part here, and then the NaOH combines with the HCl. So it's almost like you have this first and second component both happening here. And because of that, I'd expect this energy to be bigger. In fact, if you look at Hess's law, you can see I can line up these equations. I'll cross out an Na plus and an Na plus and OH minus here, OH minus here, and notice what I'm left with. NaOH plus H plus Cl minus forms H2O plus Na plus Cl minus. This really isn't a net ionic. You know that more things can cross out. But we're trying to show how reaction 1 plus reaction 3 equals reaction 2. So when we do the calorimetry with stuff, we should be showing how ultimately the delta H here and here should add up to equal the delta H here. And that's what we're going to show in our calculations. Okay, so let's go to some of those calculations. And there's a couple assumptions. We're assuming we're going to be doing these reactions in a calorimeter. Looks like a styrofoam cup. I'll double cup it. There's a thermometer here. And essentially, we start out at a temperature and we stir it. And we go till the highest temperature reached, and then it usually maxes out and starts dropping back down. Okay, that's what we're going to do to get our temperature differences. No energy is lost to the surroundings during the experiment. We know that some will be lost in actuality, but we'll assume that's small. The heat capacities for HCl and NaOH solutions are the same as that for water. We're going to say 1 calorie per gram degree Celsius. Notice I'm going to use calories for all this. In your lab, you're going to use kilojoules, but really it's just multiplying by 4.18, and that's the only difference there. And we're going to assume these densities are going to be 1 gram per milliliter. They're close. They're a little bit thicker than water, so they'd probably actually be a little bit higher, but those are the assumptions we're going to use. Okay, so let's look at this. This was the first reaction. We actually put in about 2 grams. I think that was the instructions. Let's say I exactly put in 2 grams. I can convert that to moles. My temperature change went up by 4 degrees, but I have my thermometer reads to the nearest degree, so I'm going to estimate one place past that reading. The heat energy released is interesting. What got heated up? Well, the whole solution did. So the 100 milliliters of, I used 100 milliliters of water, which would be 100 grams, and then the 2 grams of stuff. So all of those things got heated up. So be careful. A lot of times there's mass confusion about this. So include the mass of both the solution, which in this case was 100 milliliters of water, and also the grams of the NaOH, which is a smaller factor here. Okay, if I know calorie, then I just take CM triangle T. I figure out calories, I can convert to kcals. Well, that's how many kcals that ultimately was produced when I used 2 grams of NaOH. What if I used 1 mole of NaOH? How much would that be? I just take my kcals divided by moles, and this is what I came up with. Whenever I use a delta H for an exothermic reaction, the sign becomes negative. So I put that sign here, and I did dip back to 2 figures because I was limited by the 2 figures in my temperature change. So that's why I dropped back at the end in that calculation. I could also write this and say 1 mole of NaOH breaks up into 1 mole of Na plus 1 mole of OH minus and releases 8.2 kcals. Okay, just going to go to reaction 2, show that same type of thing. We have the mass of NaOH. We convert that to moles. Our temperature change was much bigger. It was 11 degrees. In this one, I still had NaOH, and I had 100 milliliters of hydrochloric acid. However, hydrochloric acid is assumed to have the same density of water, so it still ends up being 100 plus 2 or 102 grams here. I get my calories, convert to kcals, divide by my number of moles, and notice with the bigger temperature change, same number of moles, I get a bigger number of kcals here. Notice the negative sign here. Notice 3 figures here, so I carried 3 figures in what I'm going to do, what I did there. The third reaction is kind of interesting because I have 2 solutions. I have 50 milliliters of NaOH and 50 milliliters of the acid. So I take my liters times molarity of NaOH, and I get 0.0500 moles. Now, it just so happened the acid or the base wasn't a limiting reactant. I had 0.0500 moles of each one. So everything supposedly reacted. I get my temperature change, the heat energy released. There's no solid sodium hydroxide. I just have the 100 milliliters of solution, 50 from the NaOH and 50 from the HCl. So that ends up being 100 grams. I get my numbers here. I figure out my heat energy, divide by my moles. I get my kcals per mole reaction. And remember, delta H is negative there. Now, just comparing it, we said 1 and 3 should be near number 2 when we talked about it. Negative 12 in number 3, negative 22 in number 2, and negative 8 in number 1. It looks like it's going to be 20 points, negative 20 point something, negative 22 point something. So that seems reasonably close, around a 10% error that we have going on here. So that is just a little bit of a Hess's law example, and then some of the specific calorimetry and calculations, which is going to parallel pretty closely to some of the things that you're going to be doing for your Hess's law lab. Thank you.